Swayam Prabha. Digital India. Educated India.
Welcome to the 34th lecture of the open course on diffusion in multi-component solids. In this lecture, I have presented the derivation of Einstein's equation, which is also known as Einstein-Smoluchowski equation. This equation established the physical significance of the diffusivity term as a measure of mean square displacement per unit time. So, we are going over the theory of random walk. In the last class, we derived the expression for mean square displacement of a large number of particles when each particle makes n jumps. Why do we need this mean square displacement, and how is it related to the term diffusivity? We will see it today. So, we are considering an ensemble of large number of particles at x equal to 0 at t equal to 0. Now, these particles are undergoing random walk, and so this distribution will spread in space with time. So, if we track the individual particles, each particle would have made some net displacements in time t. So, if we define this net displacement as r bar, and if we write r bar equal to x I cap plus y j cap plus z k cap, then x, y, z are the projections of r bar on x, y and z axis. So, if we consider the x direction, the projection here would be x. We are denoting this projection as capital X, and r square would be given as x square plus y square plus z square. So, what Einstein did, he defined a function phi of delta tau, which defines the probability that the particle has increased its x coordinate by delta in small time interval tau. In today's convention, we would like to write it as phi of x tau, where the capital X is the projection of the net displacement vector r bar on the x axis. So, phi of x tau is the probability that a particle has increased its x coordinate by x in small time interval tau. Now, what is this phi of x t? To understand this, if we consider that at t equal to 0 there were n particles at x equal to 0, then the number of particles at plane x equal to x after time tau would be given by n times the probability that a particle travels a distance whose projection is this capital X in time interval tau. So, n times phi of x tau. So, if we consider plane of concentration at x, that is denoted as C at x, and if we want to find out the concentration at x at a time t plus tau in terms of the concentration at x minus x at time t, that can be expressed as C at x and t plus tau should be equal to C at x minus x, note this small x and capital X, at t times phi of capital X and tau, and we have to sum this over all capital X, right. So, if we consider the continuous values of x, we say the integral from minus infinity to plus infinity dx. So, this capital X varies from minus infinity to plus infinity. So, this is simply the balance equation. Now, we can expand this C at x t plus tau as C at x and t plus tau times dou c by dou t plus tau square by 2 times dou 2c by dou x2 and so on. And inside the integral we can similarly expand C of x minus x t, that would be C at x and t minus x times dou c by dou x plus x square by 2 dou 2c by dou x2 and so on times phi of x tau dx. Now, we are considering very small interval tau. So, on the left hand side of this equation we can ignore the terms involving tau square and onwards. We can write approximately left hand side as C of x t plus tau times dou c by dou t, and as tau tends to 0, most of the distribution would tend to be segregated towards x equal to 0, right. So, on the right hand side we can ignore the terms higher than x square, right. So, we can write on the right hand side minus infinity to infinity C of x t minus x times dou c by dou x plus x square by 2 times the second partial of c with respect to x times phi of x tau dx. Remember, this integral is with respect to the capital X, which varies from minus infinity to plus infinity. So, at any given position of small x and at any time t, we can take these terms C of x t, dou c by dou x and dou 2c by dou x t outside the integral, right. So, c dou c by dou x and dou 2c by dou x2, these terms are fixed. So, if we take those out, we can write c at x and t plus tau times dou c by dou t equal to C of x t integral minus infinity to infinity phi of x tau dx minus dou c by dou x integral minus infinity to plus infinity x times phi of x tau dx plus dou 2c by dou x2 integral x square by 2 phi of x tau dx. Now, this integral, what should be the value of this integral? Integral minus infinity to infinity phi of x tau x, this should be capital X. Remember, phi is the probability that a particle has increased its x coordinate by capital X in time interval tau. So, if we take the summation of these probabilities over all possible values of x, it should be unity 1, right. So, this integral should be 1. What about this integral x phi of x tau and integral x square by 2 phi of x tau? So, let us consider n particles. So, in time interval tau, let us say out of n, n1 have increased their x coordinate by x1, n2 have increased their x coordinate by x2, and so on. Right. So, if we write the average of nth power of x, that should be equal to n1 times x1 to the power n plus n2 times x2 to the power n, and so on. This is divided by total number of particles n, right. Now, if we consider this term n1 by n, what is this? Is the fraction of particles which have increased their x coordinate by x1. In other words, it is the probability that a particle has increased its x coordinate by x1 in small time interval tau, right. So, this way we can write this as x1 to the power n times phi of x1 tau plus x2 to the power n times phi of x2 tau, and so on. And if x varies continuously, we can write this as an integral, x taking values from minus infinity to infinity, x to the power n phi of x tau dx, right. So, this gives me the values of other two integrals here. So, the integral x times phi of x tau would be average x, that is the average of x projections of net displacements of all the atoms. Similarly, integral x square phi of x tau dx would be average of x square, which is the mean square displacement of all the atoms. And there is a factor of 2 here. So, if we write the c of x t on right hand side will cancel with that on the left side. So, and this tau if we take on the right hand side, we get the expression dou c by dou t equal to mean square displacement x square by 2 tau dou 2 c by dou x2 minus average of x by tau dou c by dou x. Again, for a true random walk problem, we have seen before, the mean displacement of all atoms should be 0, right, because for every atom that has made a net displacement, let us say r n I bar, there would be another atom which has made an exactly equal and opposite displacement r n j bar, that is r n j bar is equal to minus r n I bar, and the average of net displacements of all atoms should be 0. And so, we get dou c by dou t equal to mean square displacement x square over 2 tau dou 2 c by dou x2. This looks familiar. This is similar to the diffusion equation. With diffusivity d being written as x square by 2 tau. Now, this is in one particular direction that we are considering. For a true random walk problem and for an isotropic cubic lattice, the distribution is spreading isotropically, right, and we can write average of x square equal to average of y square equal to average of z square, right, and so we can write the mean square displacement r square, the average r square, as average of x square plus y square plus z square, and since average of x square equal to average of y square equal to average of z square, so we can write average of x square as average of r square divided by 3, and if we substitute here, we get for an isotropic cubic lattice d is equal to r square by 6 tau. And this is the equation that Einstein derived in 1905. So, it is called as Einstein relation, this one or this one, any of this. Simultaneously, but independently, Smoluchowski also derived a similar equation. So, it is more commonly referred to as Einstein-Smoluchowski relation, and this clearly establishes the physical significance of the term diffusivity. And what is it? If we want to describe the physical significance, it is the mean square displacement per unit time. Mean square displacement of an average atom per unit time. That is the diffusivity, and that is the physical significance of diffusivity, which was established by this Einstein-Smoluchowski relation. Now, remember, when we defined this function phi of x tau, we made an assumption while deriving this equation, and the assumption was that the function phi is independent of x and t, small x and small t. So, in a way we assume that the diffusivity is constant, the mobility is constant, it does not change with x and t, which means this expression for diffusivity is valid for absence of any concentration gradient or in presence of very small concentration gradient. So, that phi of x tau remains independent of x and t. Okay. So, this expression is valid for self diffusivity or impurity diffusion, but it is not valid for a case of diffusion under strong concentration gradient, or in other words not valid for interdiffusion. Right. We have seen for interdiffusion we need more than one diffusion coefficient because there are multiple concentration gradients. Okay. So, this is the physical significance of the term diffusivity. Now, we can make a substitution. In the last class we derived the expression for mean square displacement. So, mean square displacement r square average was given as n lambda square, where each particle has made n jumps. Now, if gamma is the successful jump frequency then gamma is the number of jump an average atom makes per second, right. So, in time interval tau, the total number of jumps made by an average atom would be gamma times tau, right. So, we can write r square is equal to gamma times tau lambda square, and if we substitute in the Einstein-Smoluchowski relation, we get d is equal to gamma tau lambda square by 6 tau for any cubic lattice. So, tau tau will get cancelled and we get the expression d equal to 1/6 gamma lambda square. So, we get the same equation that we got a few classes back based upon the simple jump frequency model, right. So, the point to take away is the Einstein-Smoluchowski relation established the physical significance or the theoretical meaning for the term diffusivity. The diffusivity is a measure of mean square displacement per unit time. Okay, and that is why the unit of diffusivity is meter square per second. The mean displacement is not a good measure, we have seen, but mean square displacement is, and so we say mean square displacement per unit time, that is diffusivity in meter square per second. Thank you.